It's my pleasure to introduce Kate Follette, an assistant professor of astronomy here at Amherst College. Previously, she was a NASA Sagan Fellow at the Institute for Particle Astrophysics and Cosmology at Stanford University. Kate received her PhD in astronomy from Steward Observatory in December of 2014. Her research focus is on the detwinkling of stars in order to hunt for exoplanets. Kate teaches courses in physics and astronomy with an emphasis on quantitative literature across the undergraduate curriculum. So I'll hand it over to her.
Hi everyone, it's a pleasure to be here today to talk to you a little bit about the science of exoplanets, so planets around other stars, which I have the privilege of working on. And it's, we kind of just passed the 20th anniversary of the first discovery of an exoplanet. So I see some young people in the audience here, and so something that was purely science fiction 25 years ago is now a reality that I'm basing my career on. So just something to think about. So to get started, I'd like to take you back to the year 1994. And so just to kind of put that into perspective relative to today, whereas the top song of the year was Ace of Bases, The Sign, which is what this is. And I'll just mute it. Maybe we could turn off the sound. We couldn't turn it any lower than this. Okay, thanks. So I hope that put you in the mood of 1994. Just a couple of other things. So Will Smith is today playing very serious roles, but in 1994 he was starring in my favorite TV show of the time, The Fresh Prince of Bel-Air. And rather than being the mom of a 3-year-old, I was in the 7th grade when the first exoplanet was discovered. So in that time, now that you're kind of in this mindset, what do you think people thought of when they thought of planet? Or exoplanet wasn't even really a thing at the time. What do you think they thought of?
Something from outside of this planet rather than an actual planet.
Sure. What kinds of references in popular culture do you think people thought of when they thought of planets?
Star Trek.
Star Trek. Star Wars, Superman, all kinds of sort of our popular conception of what planets around other stars might look like. Sort of looked like this is a smattering of things. And actually I've included one that was somewhat creative, but in general, 3 of these are just solar system planets, right? We imagined that when we found planets around other stars, they would look pretty much exactly like the planets in our own solar system. The most creative we got, and I'll say that we actually, such planets do exist, was thinking about planets that might orbit a binary star system, like Tatooine in the Star Wars series. So for the first half of this talk, I'm going to kind of give you a history of the discovery of exoplanets, and I'm going to show you a bunch of plots like this, so I want to kind of break this one down to start with. So on the x-axis here, we have the period of the planet's orbit in years on a log scale. So going from 1,000th of a year, which is about half a day, to 1,000 years in orbit. And there's a direct analog, so you can directly translate the period of a planet's orbit to its distance from its star through Kepler's third law of planetary motion. So this directly translates to a distance from the star with the very nearby planet. So essentially the star that the planet is orbiting is along the y-axis here, to very distant planets to the right. And on the y-axis, you have the mass of the planet in Earth masses. So 10 to the 0 here, or 1 Earth mass, is here. And we're going from about 1,000th of an Earth mass to 10,000 Earth masses. And that's about 10 times the mass of Jupiter. So at the very top of the diagram here, as you're looking at these, you should think these are kind of the things that are, you could debate whether to call them planets or not. They're so much more massive than Jupiter. We might more properly call them brown dwarfs, which are kind of failed stars. But we're not going to draw that distinction in this talk. And throughout the talk, you'll see a year here and a planet count underneath it in red. And the person who developed these, I lifted this from an astronomer named Hugh Osborne, who designed this animation. So you'll see his name on here throughout. So if we go even farther back than 1994, all the way back to 1750, why do we have planets on this diagram? What do you think these are?
The solar system.
these are the solar system planets, right, which you can actually see if you look at 1 year and 1 Earth mass is Earth. At about 5 years and 100-ish Earth masses, or just under 1,000, sorry, Earth masses, is Jupiter, Saturn, Mars, Venus, and Mercury. So those are the planets in our solar system. And in 1750, that is actually all that we knew about, were the 5 naked eye planets that you can see in the night sky and Earth. So what happened in the late 1700s was sort of the advent of the telescope. It was broadly applied to searching the outer solar system. In particular, perturbations in the orbit of Saturn suggested that there might be outer planets in the solar system. The location of those outer planets were predicted, and that led to the successful discovery of Uranus by William Herschel. Similarly, perturbations in the orbit of Uranus were monitored for a while and led to the discovery of Neptune. And then we kind of entered a period where there were no new planet discoveries for quite a long time, until 1930, when Clyde Tombaugh discovered what's now called the dwarf planet Pluto. And I don't want to get into why that is in this talk, but you could, of course, ask me about it in the question and answer section if you'd like. And then nothing. So we could walk through this in 5-year increments, and there would be absolutely no development in our understanding of planets in our solar system or anywhere else until you got to 1995, when a very exciting thing happened, which was the discovery of the first planet outside of our solar system. So this was the planet 51 Pegasus b, or 51 Peg b. It's orbiting a sun-like star that's about 50 light years from Earth, and it's about a half Jupiter mass planet that orbits on a 4-day period. So it's way in the upper left of this diagram, and I'll talk a little bit more about these very strange planets that are kind of 51 Peg analogs a little bit later in the talk. But this was very exciting. So we had finally successfully discovered a planet outside of our solar system, and it was using this method called radial velocity. So in this first half of the talk, I'm going to kind of introduce the 4 main ways that we discover exoplanets and just briefly introduce you to how they work. So this was discovered via the radial velocity method, which is also called Doppler wobble. And the basic way that the Doppler technique works, let's see, this should play. No. Should play automatically. Is if you imagine a planet orbiting a star, we're going to kind of exaggerate this. So first of all, we're going to look at it nearly edge-on, and we're going to inflate the mass of the planet to exaggerate the effect that happens due to the gravitational influence between the gravitational interaction between any 2 bodies with mass. They orbit, we usually think of the smaller object orbiting the larger one, but what actually happens is they both orbit their common center of mass. So the larger the planet is, the farther away from the center of the massive object, the center of mass is, and the bigger the wobble as the star, in this case, orbits the common center of mass. So the bigger a planet is, the bigger the wobble. The way that actually works, so we of course don't observe the planet at all in this case, we observe the star. And what we actually observe is in the spectrum of a star, so if we spread the light of a star into its component colors, there are characteristic lines where gases in the atmosphere of the star absorb light of certain colors. And we see those lines shifting towards the blue end of the spectrum and then towards the red end of the spectrum, doing what we call blue shifting and red shifting. This is the Doppler effect for light. As the star moves towards Earth, we get a little blue shift in the lines, and as it moves away, we get a little red shift in the lines. And the period of that oscillation is the period of the planet's orbit around its star. So we can infer its period, and based on the magnitude of that wobble, we can get its mass. So that's kind of technique number 1. And in the 5 years that followed that, up to the year 2000, this technique really took off. And we had about 20 successful radial velocity detections by the time we got to 2000. And one thing I'd like to highlight about them is essentially what happened is we were able to monitor. So here are the weird, couple day period planets. Radial velocity campaigns, as they continued, were able to detect planets of comparable mass out to 10-year or 1 to 3 year periods over that time scale. So the technique was around long enough that we were pushing this way into longer and longer periods. Of course, also in 2000 was the first successful detection, actually in 1999, of a transiting exoplanet. And the way that technique works is it's sort of comparable to how many of you saw the transit of Venus in 2012? Okay, so what happened when you saw the transit of Venus, right, is Venus passed in front of the disk of the sun relative to our line of sight. And from Earth, you could actually see that. It was pretty cool. For those of you who missed it, I'm sorry, it was your last opportunity for a very, very long time. But what happens when a planet passes in front of its star, a star that's much more distant, is whereas the star had kind of a constant brightness level beforehand, as the planet passes in front of it, you get a little dip. And then as the planet comes out from in front of the star, you get it returning to the constant brightness level of before. So you get a little dimming of the light of the star, and we infer from that the existence of a planet of a certain size, right? Because what we're really measuring is how much of the star's light is blocked by the planet. So this was also quite successful over in intervening years. So up to 2004, we discovered about 10 transiting exoplanets. And 2004 was a big deal in the exoplanet field because we detected two other it was the first successful detection using two other techniques. So the direct imaging method is what I do in my work, and I'm going to talk about it in a lot of detail in the second half of the talk. So for now, I'm just going to tell you direct imaging is exactly what it sounds like. It means we take a picture of the planet. So we take a picture of it, we can directly isolate the light from the star from the light from the planet. And the other method here is microlensing. So let me explain how that works, and it has this horrible name. All these planets have very horrible names, so they're not creative at all. Planets around other stars are always named with the name of the star plus a lowercase b for the first planet, c for the second planet, d, et cetera, et cetera. So these are star names, really, with a b on the end for the planet. So how does microlensing work? Microlensing is essentially a relativistic effect. So when you have a background star and a foreground star that are both perfectly aligned relative to Earth, what happens is the light from the background star will get magnified as it gets bent around the foreground star, if they align perfectly. So whereas the background star had some constant brightness, during this microlensing event, you'll get an increase in brightness as the image is magnified. Apparent brightness of the background star. It's of course not any brighter than it was before. So the reason this technique took off in the early 2000s is because that's when we started doing very systematic monitoring of the brightness of objects in the night sky. So lots of campaigns where we're taking images nightly or even hourly of stars and looking for changes in brightness like this. So what happens if that foreground star has a planet orbiting it is instead of seeing this smooth perturbation, you get a little bump on top of it. So you get, the star brightens, 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 it starts dimming, and then as the planet also lenses the light from the background star, you get a little blip in this light curve that corresponds to the planet. This can happen even for pretty widely separated planets as long as it is also, both the planet and the background star are aligned. So you sometimes get the blip happening outside of the main lensing event. And we can even with this method detect what are called free-floating planets. So sometimes you just see a low-mass blip where you coincidentally had some planet that's out in between stars in interstellar space, perfectly aligning with a black background star and magnifying it slightly. So that's the microlensing method. And at this point, so we're at 2005 to the 2010 window. At this point, all four of these methods have been reasonably successful. They all have kind of 5 to 10 detections or more. And there was sort of a steady rate of exoplanet discoveries between 2005 and 2010, but the whole landscape changed in 2010 with the launch of NASA's Kepler spacecraft. So Kepler was specifically designed to locate transiting exoplanets. And here's what happened. So now I'm just going to go through in 1-year increments. So, oh, sorry, I forgot. I was going to tell you about Kepler first and why it was special. So the reason that Kepler was so unique and important is because essentially before 2010, when Kepler was launched, we were doing all of our transiting exoplanet detections from the ground using big telescopes. And this is essentially what it looked like. So in the background here, this solid line that you see is kind of the theoretical sort of exoplanet light curve, transiting exoplanet light curve. So you get this dip. But this is what the real data looked like from the ground. So it's very noisy. You can see that there's a real thing that happened here, but it's very difficult to detect. This is real data from the Kepler spacecraft of the same transiting exoplanet, right? So you drastically decreased that noise. So you're able to see much smaller transits.
Is that noise coming from the atmosphere?
Yes, mostly the atmosphere. Even beyond that, so here's another Kepler light curve. So this is the sort of main light curve. You see these deep transit events. Here are two of them. If I zoom in on this, what looks like perfectly flat, you can see it actually has a shape. And there's a second dip right in between the two main ones, which is actually what's called the secondary transit. So not only is the light from the star blocked when the planet passes in front of it, but actually the light from the planet is blocked when it passes behind the star relative to our line of sight. So this little dip here is us losing the light from the planet itself. And this curvature here is our sort of changing phase of the planet, kind of like the phases of the moon. So when it's in certain orientations, more of the illuminated part of the planet is facing Earth. And so you see that it reaches a maximum here, and then it passes behind the star. So the exquisite sensitivity of Kepler completely changed the field of transiting exoplanet detections. But that's, of course, not what I do. So I'm a direct imager. Oh, first let me just show you the progression and proliferation of transiting exoplanet discoveries following the launch of Kepler. So here's 2011, 2012, 2013, 2014, 2015, which is when this animation where I stole this ends. And actually when Kepler died around 2015, when it lost one of its reaction wheels. So the main mission returned all of these transiting exoplanets. So that was the picture as of 2015. I recently, with my students in a class that I taught this past semester, called Practical Astronomy, which is an astrophysical techniques course on computer programming and statistics, but is effectively a sort of data science for astronomy course. This database of exoplanets is a great thing to have them play with because it's always changing and there are lots of things that people haven't found yet. So we developed a new version of this visualization with an updated database. And you can see that there are actually there have been quite a few more successful direct imaging detections in particular, and also microlensing. But actually the rate of transiting exoplanet discoveries has not continued at the same rate as it was because the Kepler mission died. And here again are our solar system planets for reference. So this is what the landscape looks like in 2017. And I want to point out a couple things about it before I tell you about direct imaging. So the first thing is, here are all of our solar system planets. You'll notice we aren't detecting really any analogs to our solar system planets yet. So the technologies, all four of these technologies, are not quite capable of detecting solar system analogs, with the possible exception of Jupiter. So you see all of these are kind of off in a region where there are none or very few successful discoveries of exoplanets in this kind of separation mass regime. And if that's not telling us that we're weird. The entire history of astronomy, in the entire history of astronomy, the Earth has never proved to be special. Okay, we don't orbit a special star, we don't orbit in a special place, we're not the center of our solar system, we're not the center of the galaxy, we're not the center of the Milky Way, we're not the center of the universe. Our operating assumption has always been that these are sort of typical planets, that there's no way our solar system is particularly unique. And so what I want you to take away from this is the idea that right now, the region of parameter space that we're probing are kind of the oddball planets that the universe creates. We're probing only the very edges of the distribution because it requires quite exquisite sensitivity for all of these methods to detect planets that are real analogs of the ones in our solar system, with the possible exception of Jupiter, which is kind of right at the edge of this cloud of things that are probably, approximately Jupiter analogs. Another thing that I want to point out here is among the planets that we've found here, there are kind of three particularly interesting populations for which we have no analogs in our solar system. So the first one are these 51 peg-like planets called hot Jupiters. So they orbit inside of the orbit of Mercury in our solar system and are of comparable mass to Jupiter. And conventional wisdom says we have no idea how things like this could even form, because we think that gas giants, like the gas giants in our solar system, you'll notice are all out at 5, 10 AU or more. By the way, an AU is an astronomical unit, the separation between the Earth and the Sun. And Jupiter is at 5 AU in our solar system. So we think that gas giant planets like Jupiter can only properly form when there are ices present. So they can't form in the very hot inner regions of a solar system. So how these hot Jupiters got here, we have absolutely no idea. Strangely, it appears like these aren't destructive events. So you could imagine something like Jupiter migrating into the inner solar system and kind of gobbling up any intervening planets along the way. But hot Jupiters, a lot of them actually have companion planets in their systems. So we haven't arrived at a perfect picture for how these exist, although it does probably involve some kind of migration from the outer solar system to the inner solar system. And that's not even something that we had thought was possible before we started looking for exoplanets. Another kind of interesting population are the ones that I study, which are out here. So these very distant super Jupiters, so planets that are more massive than Jupiter and in the very, very outer solar systems, hundreds or even thousands of AU. So kind of beyond the regime where we think there must have been material to form planets around the early versions of these stars. And then maybe the most interesting of all are these planets that are in between the mass of Earth and the mass of Uranus and Neptune in our solar system, which are, after all, very different planets, right? These are all rocky planets. These are all gassy planets. So we kind of expected when we were first doing exoplanet censuses that we would see a gap somewhere in here. The universe creates a lot of rocky planets. It creates a lot of gas giant planets. Those are kind of, common formation modes. But the fact that there's a large population of planets that lie in between these, and in fact, recent statistics from Kepler suggest that this might be the most common type of planet in the entire universe, is something in between the mass of Earth and the mass of Uranus and Neptune. So we call them super-Earths, generally. But we don't actually know if these are scaled up rocky planet versions of Earth or scaled down versions of Uranus and Neptune. Are they mini Neptunes? Are they super-Earths? That kind of remains to be seen. And the answer is probably a mixture. That there's a regime where a planet could be either rocky or gassy, depending on where it was formed. Sort of the last thing I want to point out about this place that we find ourselves in discovery of exoplanets is that right now we're finally reaching a place where, because of this proliferation of discoveries, there is a fair amount of overlapping parameter space. So each sort of you see the different types of points are all clustered in different areas of the diagram. So for example, the directly imaged exoplanets are all very distant and very massive. That's actually just an effect of the technology. We can best detect planets that are very distant from their stars and very massive. And we're pushing in and down for direct imaging. Radial velocity is generally limited by there's sort of a mass floor. The wobble of the planet gets smaller as the planet gets less massive. So it's difficult to detect things at the bottom of this diagram. It's also difficult to detect very distant ones because you have to wait. If the pattern of radial velocity is the starlight is red-shifted, then blue-shifted, red-shifted, then blue-shifted, and you want to wait for it to complete, the planet to complete a full orbit, you have to monitor the spectrum of the star and look for that wobble over 10-year plus timescales if you want to get out to sort of this region of the solar system. And transiting exoplanets, the probability of a transit happening is much, much higher in the very inner solar system and drops off kind of precipitously as the planet gets farther away from its star. It's just a geometric probability, actually, if you think about it. The farther away it is, the lower the probability that it'll line up perfectly relative to your line of sight from Earth. And so each of these is detecting planets in different parts of parameter space, and they're becoming very complementary. And in fact, we're reaching a time when there's some overlap here. So there are planets now that are capable of being discovered by both radial velocity and direct imaging. And there is a whole slew of planets that have been detected via both transit and radial velocity. And if you think about that, that's actually super powerful because transits, as I said, measure the size of the planet, and radial velocity measures the mass of the planet. So if you have a mass and you have a size, what else do you have?
Density.
Density, exactly. So you have some way of answering questions like the one I posed before about what these super-Earths really are. If you have the planet's bulk density, you can start to answer questions about what it's made of. And there are some similar sort of complementarities between direct imaging and radial velocity that I can get into. So in this sort of second half of the talk, I want to talk about the direct imaging method and what I do more specifically, what we're doing here with my students. So direct imaging is, like I said, exactly what it sounds like. We see directly rather than indirectly. So if you think about the radial velocity and transiting detection techniques, we are observing the star and inferring the existence of the planet. I like the direct imaging technique myself, partly for sort of the visceral satisfaction of seeing the planet, right? It's sort of incontrovertible that these are planets. We're seeing the light emitted directly by them, and that's satisfying. These aren't, beautiful images like we've gotten used to seeing from Hubble, but they're beautiful scientifically, and I hope to convince you that by the time we get to the second half of the talk. So these are just some of the directly imaged exoplanets. These are detections from a campaign that I work on called the Gemini Planet Imager Exoplanet Survey. So we have about 300 nights of telescope time on the Gemini telescope, 300. We have 600 targets, so 600 hours of telescope time. On the Gemini telescope in Chile, Gemini South telescope, which is a 8-meter telescope in the Atacama Desert in Chile. And here are some of the planets that we've detected. These three were already known before the start of our campaign. And here's one that we discovered that I think is particularly exciting for reasons that I'll tell you about in a minute. And we, of course, for free, get a bunch of brown dwarfs, which are also very interesting in that they lie between the mass of planets and the mass of sort of low-mass stars and are kind of interesting intermediate objects, scaled-up versions of the kinds of planets that we're discovering, and probably formed via the same mechanism. So the dividing line between the two is a bit arbitrary. So if we want to do this, how does it work? Sort of what are the obstacles that we have to overcome in order to be able to take an admittedly kind of ugly image here? So I'll say that when I show you images like this of these planets, I've always masked the residual light from the star at the center. So there's what's called a software mask, or in some cases even a hardware mask, so an actual physical optic that's blocking some of the light from the star. And then we do a lot of post-processing using sophisticated computer programs that are aimed at identifying the light from the stars. So you always see this kind of mess at the center of the images, and that's residual starlight, and the things with the arrows here are planets. Those don't show up in the images, obviously. The universe doesn't tell us what's really a planet and what is an artifact in our data. So the first obstacle that we have to overcome in order to be able to do this is contrast. So I'm going to just kind of do a little scale model, an analog for you. So if I'm comparing, in this case, the sun to a lighthouse. A lighthouse is something that you all probably have experience with, a very bright thing. Yes. So the sort of relative brightness of Jupiter relative to the sun is a factor of 10 to the 9. So it's 1 billion times fainter than the sun in reflected light. The analog there is approximately 10 bioluminescent algae have a brightness that's about 1/billionth of the brightness of a lighthouse. We actually can't do this today. We can't do a contrast of 10 to the 9. What we do is a clever trick. So we look for hot, young versions of Jupiter. So they're young. They still have residual heat from the formation process, and they glow brightly in the infrared. So in the infrared, the contrast is only 10 to the 6, a factor of 1 million times fainter. And that's approximately the same as the difference in brightness between a firefly and a lighthouse. Not so hard, right? Well, actually it is, because, so the solution for this contrast problem is partly coronography, which is just this idea that you can block the light from the star to the extent that you can. This requires a physical optic, and it's not as simple as it seems, right? You would think, okay, whatever, just slap something in and block the light from the star. But as many of you may remember from intro physics classes that you took here, light diffracts around solid objects, right? So I can put something in to block the light from the star, but it will bend around the thing that I placed there. So there will always be residual starlight in my images, even if I have something blocking the physical location of the star. So the classic analog to this is, if you want to see something in the bright sky or in this room, if I were looking for something near that bright light there, I would maybe block the light from the star to allow me to see fainter things next to it. This is a classic picture, kind of just an analog. That's Earth right there. So Saturn is blocking the sun in this picture so that you could see reflected light from Earth from beyond the orbit of Saturn. So coronography helps. And I'm going to gloss over all of it, but we also use a lot of post-processing, like I mentioned. So essentially linear algebra techniques to remove as much of the residual starlight that's diffracted around the coronagraph as we can. But there's actually a second obstacle, which is an angular separation obstacle. And I apologize, I haven't updated this since I was at Stanford. So I'm going to pretend, I'm going to use the location between Stanford and where my parents live in Minneapolis as an example. So if I go 1,500 miles away from Stanford to where my dad lives in Minneapolis and I tell him to point his telescope at the lighthouse at Santa Cruz, then the analog here, so you remember my firefly lighthouse analogy, the separation between the firefly and the lighthouse is 20 feet, right? So the real analog to what we're doing is we're separating the light from a firefly from the light from a lighthouse from 1,500 miles away. So I hope that seems impressive because it's a huge technological advancement that we've been able to do this. And the way to overcome this angular separation obstacle is to use this very cool technology called adaptive optics. I think this should play. Okay. So adaptive optics allows us to correct for the blurring effect of the Earth's atmosphere. So whereas we originally have a blurry image, it allows us to take clear images. And I'll explain how that works in a second, but I just wanted to highlight that this is kind of what it looks like. Adaptive optics off, you're looking towards the center of our galaxy. You see no individual stars. You turn adaptive optics on, and you see that there are a whole bunch of individual stars in that region in the inner galaxy. It's a specifically interesting region around a radio source called Sagittarius A star. And if I track the orbits of those stars, resolving the individual stars with adaptive optics and tracking them with time, you can see this technology enabled one of what I think are the most important discoveries in astronomy in the recent history was the measurement of the mass of the supermassive black hole at the center of our galaxy, which was done using adaptive optics, tracking the orbits of these stars, and again, just applying sort of Kepler's laws. So if I know the period of this, I can figure out the mass of the object that it's orbiting. And it turns out to be millions of solar masses. So it's a supermassive black hole at the center of the galaxy. These stars are all orbiting nothing, no source of optical light at this location. Just as a brief aside, you eventually might be getting eye exams using adaptive optics too. So this is adaptive optics imaging of the human retina. And when the adaptive optics turns on, you see individual cones in the eye. It's actually the only way to image individual cones in the eye in a living eye without dissecting and isolating the cells from the retina. Is because you're imaging through ocular fluid, and there are lots of kind of changing optical deformations in your eye. It turns out if you want to study and image the human retina, you have to use adaptive optics. So how does it work? So the basic idea is that light from a star comes into the atmosphere in the form of a plane wave, so it's flat. And it reaches a layer in the atmosphere that's turbulent. And the way that I would picture it working is essentially that within each turbulent patch of atmosphere, this wavefront is locally flat, but between neighboring patches of atmosphere, it may end up corrugated. So each one bends. It works kind of like a lens. It may refract the light a little bit in different directions. And what comes out at the end is no longer a flat wavefront, but once it passes through this turbulent atmospheric layer, you get this corrugated or distorted wavefront. So how do you fix that? Here's my telescope surface. You can see how this would end up being blurry in that if I bring this corrugated wavefront to a focus, it'll come to a focus at a bunch of different places near one another, and you'll have a big blurry image. What I want to do in order to create a crisp, clear image, high-resolution image, is to flatten it again, which I can do if I can detect the way that this is corrugated, and I won't talk about that in any detail. I can attach magnetic actuators to the back of my telescope surface, and I can deform it to compensate so that when the light from the atmosphere, the distorted light from the atmosphere, bounces off that corrugated telescope surface, you get a re-flattened wavefront and a crisp, clear image. I'm glossing over a lot of complex technological things, but that is essentially how it works. The other cool thing about this is that this happens 1,000 times a second. If you want to effectively correct for the blurring effect of the Earth's atmosphere, it not only, it changes quite rapidly in time. So this only works effectively at infrared wavelengths if you can do it 1,000 times a second. But it allows you to do things like this. So I promised to tell you why I thought that this new discovery from the Gemini Planet Imager was important and interesting. And the reason is that this is almost a solar system analog. So it's a planet about the mass of Jupiter at about the orbit of Saturn. So it's at the very kind of edge of what we are capable of detecting. And you can see that we have some room to grow here. We could have detected this same planet a little bit closer to its star, and probably a little bit fainter too. So this kind of represents where I think direct imaging is going, is towards things that are really solar system, sort of Jupiter analogs. The other cool thing about this new generation of direct imaging instruments is that we're not actually just taking an image like this, we're taking what we call a spectrum. So we're measuring the brightness of the planet at a bunch of different wavelengths. So here you'll have the images, and here's what we call the spectrum of the star. So this is just if I take all the light from the planet there and I add it up, how bright is it overall, and how is that changing as a function of wavelength on this axis. So this is wavelength, and this is brightness. If I walk through the cube here, you can see that the planet appears at certain colors and kind of disappears out here. And this is actually very interesting and important because it allows us, this is the advantage that direct imaging has over all of those other exoplanet detection methods, is not only that it's direct, but that it allows us to characterize the planets. So specifically, the shape of this spectrum is a function of temperature of the planet. So we get a measurement of the temperature, but maybe even more interesting, temperature and composition of an atmosphere are related to one another. So specifically, this is the spectrum I showed you before. So this peaky spectrum here is a result of absorption by the element methane. So it turns out the atmosphere of this planet 51 Aries is dominated mostly by the element methane, just like Jupiter's atmosphere is. And methane absorbs in kind of this window and this window. So whereas the brightness of the planet should be about here at this wavelength, it gets absorbed by the atmosphere, just in the methane absorption bands. So we can characterize the composition of the atmospheres of these planets using this method, and also their temperatures. And that's a distinct advantage to direct imaging over other detection methods. Another advantage is youth. So all of the stars that we directly imaged are young, sort of necessarily, right? I mentioned that we're imaging hot, young exojupiters. We can only detect them using current technologies if they have enough, if they're glowing brightly enough in the infrared that the contrasts are only 10 to the 6, a factor of 1,000,000. And that is interesting and important because it represents an important epoch in planet formation. So it's the planet formation epoch. These are very young planets. They're newly formed. They're kind of turbulent adolescent planets, I would call them. And they help to inform our understanding of the process of planet formation. So specifically, I'm going to draw here sort of, this is a picture from theory of star and planet formation on the left, and an actual image on the right. So our understanding of how stars and planets form is that in dense molecular clouds of cool gas and dust in our galaxy, something causes them to collapse, like maybe a neighboring supernova, to gravitationally collapse and form new stars, and we see that. An individual clump within that molecular cloud will collapse and ignite nuclear fusion in the core of this forming protostar, and then it will start to blow away the dust that surrounds it, just like these pictures of the pillars of creation in the Eagle Nebula. Eventually, due to dissipation of angular momentum, the material falling onto the star will be sort of ejected in a jet. And we see that. We see these jets. And we also see, you'll see it's kind of dark at the center here. So there's a very young protostar at the center driving these jets. And this dark patch at the center is what we call a circumstellar disk. So because the material in the cloud is spinning, it's like throwing up a pizza that's spinning, right? So the dense material of the nebula, so sort of the stuff that doesn't get directly incorporated into the star, because that patch around it is spinning, will flatten into a sort of pancake-like disk called a circumstellar disk. And we see those. And those are important because they provide the raw material for the formation of planets. You need that leftover gas and dust around the star to make the planets out of. Sort of the next thing that we see is, just disk, no jet. We see these, this is a famous, what's called a silhouette disk. So in the background is the Orion Nebula, a young star-forming region, and in the foreground here you see a dark patch around this young protostar. And what that is this disk, this circumstellar disk, blocking the background light from the nebula. So it's like casting a shadow. And here is where direct imaging comes in. We think that then this disk dissipates pretty quickly, but we don't know on what timescales, or whether it dissipates from the outside in or the inside out, or via what mechanism. And we think what's left over then are planets and these kind of remnant disks called debris disks, which are created by, once you grow the material in these circumstellar disks to kind of like boulder sized, they can start to collide and generate very small grain material. Like the zodiacal light in our solar system is what's called a debris disk. So these are the stages that we're probing with direct imaging, and they're interesting and important because they tell us how these disks dissipate and how planets form, where they form, at what times, out of what materials. We know, though, that the disk doesn't last that long. So this is the only very technical plot that I'll show you. So this is the age of various clusters. Each one of these labels is a young star-forming region, so with hundreds of stars in it. And what's measured on the y-axis here is the fraction of those stars that have a disk. So you can see that at very early ages, 1 million years, which is very short on astronomical timescales, almost 100% of stars have disks. And by 10 million years, almost no stars have disks. So we know you only have 10 million years to form planets. And all of those directly imaged, the reason I called them turbulent adolescent planets is because they're kind of this phase. So all of this planet formation has already happened, and they're kind of just still glowing with leftover heat from their formation. But of course, this era where the disk is actively dissipating is maybe the most interesting if you want to understand planet formation. So as part of my postdoc and dissertation work, I helped develop a technique to find very young protoplanets with direct imaging. So what you need to understand how this works is to know that if I look at the light of a star, so this is another plot of wavelength versus brightness. A star emits light of all wavelengths, though not in equal proportions. So it'll have some peak where it's brightest, and it'll emit light at a lot of other wavelengths. The cooler an object is, the less light it emits overall. So this is lower, this low mass star compared to this brighter star is lower overall, but its peak is also farther towards the red. Okay, so this tells you why we go to longer wavelengths for adaptive optics imaging of exoplanets. So for an object like this that's glowing, that's warm, the contrast is a little more favorable here at longer wavelengths. So if this is a factor of 10 times fainter than the star, this is a factor of 100 times fainter than the star, this is a factor of 1,000 times fainter than the star, as we go to longer and longer wavelengths, the gap here closes. And we have to, sort of the relative brightness difference between them is less severe. So that's a trick that we play. But in the sort of reason that we haven't detected any of these sort of adolescent exoplanets using sort of traditional infrared imaging techniques at in very young objects is kind of twofold. Well, really, the main reason is because the nearest star-forming regions to the sun are all probably about 3 times more distant than the average distance at which we detect these adolescent exoplanets. The adolescent exoplanets that we're detecting are what are called, they're part of what are called young moving groups, which are sort of associations of stars that were formed and then dissipated throughout the galaxy, but they all have kind of a common motion within the galaxy. So they get, stars form in star-forming regions and then they get thrown out into the galaxy in kind of a common pattern. And the nearest star-forming region, the nearest place where there are actively planets and stars forming, is 3 times farther away than that. And so that angular separation problem becomes even more severe for these young objects. If they're 3 times farther away, I have to be able to separate the light from the planet from the light from the star 3 times at a 3 times smaller separation. So at that kind of separation, the problem is, so I can find, using conventional techniques, I can look at planets that are stars that are that distant and search for planets around them. But when I get that close to a star, I can't get to contrasts of 10 to the 6, which is what's required in order to image these turbulent adolescent exoplanets. I can only get to contrasts that I've drawn up here of 10 to the 1, 10 to the 2, 10 to the 3. So here's the trick. So I could easily detect a low-mass star around a star at that distance. But I'm going to implement a trick here, which is to look for an accreting low-mass star. So if a planet is actively growing and sucking hydrogen gas onto its surface, it'll emit at a characteristic wavelength that corresponds to hydrogen gas. So on top of the spectrum of the star, there will be a big excess at one very specific color of light that might kick the contrast up to a detectable level at that one very specific color. For a planet, this becomes more difficult in that the planet itself is well below our detection threshold, about a factor of 10 to the 3. And so what we're looking for is an accreting planet where at this one very specific color, we've kicked it up just enough to be able to detect it. But at any other color, we don't detect it at all. So if you compare that to the star case, right? In this case, say if I imaged it at this wavelength and this wavelength, I might be able to see it at other wavelengths. It would be much brighter at hydrogen alpha, this particular wavelength of hydrogen. For the planet case, I expect to see it in this one particular color and not see it at all at any other color. And so that, by the way, that analog, this accreting planet analog, I'm just going to beat this, this example to death, is sort of comparable to imaging a fluorescent, 25-watt compact fluorescent light bulb next to a lighthouse. So much easier. Still at 1,500 miles away. So here's the result. So we actually found one. And again, the images aren't beautiful. But at the location here at the center of the image, we've subtracted to the extent that we can the starlight from the central star. And at a neighboring wavelength, so this is the hydrogen alpha color. At the neighboring wavelength, there's nothing. So see, there's this bright blob here, and there's nothing here. And in fact, if I do the difference, I see it even a little bit better. So this was the first case where this actually worked, where we had seen it in the star case before. So we had seen objects where we could detect it here and here, but it was much brighter here. But this was the first time we successfully found something that was emitting or detectable only at this one very specific color, which means it has to be a very low mass object. And in fact, it was a planet that had been predicted using another method, and at a contrast of about 10 to the 3, and a separation that's similar. Sort of this is between Uranus and Neptune in our solar system. Sorry, in between Saturn and Uranus in our solar system. But well within this disk of material. So there's still a disk around this star. It's just a few million years old. And we think that this is what we're doing is actively imaging the process of planet formation in this disk. So I just have a couple more slides. So I wanted to just say that this is ongoing work, and Amherst students are involved in this. So we've so far published 3 of the objects in this survey that I've conducted. 2 Amherst students were co-authors on this paper that I just published on this object. And I have accumulated data on a bunch more objects where we're going to look for these objects, which I have 4 students coming to work on this summer. So we're hoping to find a few more things. And we're calling it the Giant Accreting Protoplanet Survey. So if I just go back to this picture here of all of the planets that we've discovered so far, here is that 51 Eridani b, this planet that we discovered with the Gemini Planet Imager Exoplanet Survey. It's kind of the closest analog to Jupiter that we've discovered yet with this method, and very close to sort of the types of objects that are detectable with the radial velocity method today. And lit calcium-15b, in addition to being sort of the youngest of all of these, of actually all of these, this is kind of the youngest successfully detected planet. It's also getting close to this regime in the inner solar system where we might be able to detect the planets via other methods. So whereas sort of this 1995 to 2005 era was the golden age of radial velocity exoplanets, and then with the launch of the Kepler mission, sort of the past decade has been the golden age of transiting exoplanets. Not that either of these techniques have gone away, but there was a big proliferation of successful detections in these decades. I think that current technology is placing direct imaging as kind of the next big frontier in exoplanet detection. And specifically, whereas today we're detecting these things that are a million times brighter or a million times fainter than their host stars and separated by just tiny fractions of a degree, there are a number of missions that have been proposed, some of which are being built, some of which are imminently to be launched, that are capable of doing this kind of direct imaging from space. And this extra stability that affords will allow us to push towards sort of the ultimate goal for people like me who work in this field, which is to try and image truly Earth-like exoplanets. Sort of this classic, this is I don't know how many of you are familiar with it, but this is, I think, one of the most important images ever taken, which was taken by the Voyager spacecraft as it was exiting our solar system. Carl Sagan actually convinced the mission team to turn it around and point it at Earth and take an image of Earth from out beyond the orbit of Neptune. And so that little dot there is Earth from the edge of our solar system. And that's what we're working towards, right? Because if we can isolate the light from an Earth-like planet and separate it into its component colors, we can characterize its atmosphere. We could even potentially look for biosignatures in its atmosphere. Look for things that are not in equilibrium in its atmosphere that might be generated by living organisms and things like that. And so I guess I'll kind of, and of the 3 sort of missions that are being contemplated for the next decadal survey in astronomy, which is when the entire astronomical community gets together and sets the priorities for the next decade, 3 of the 4 will probably be capable of doing this kind of thing. 2 of them are specifically aimed at detecting biosignatures in Earth-like directly imaged exoplanets. So I think that this field is really rapidly advancing, and you'll hear a lot more about it in the next 10 years or so, or at least I hope so. So thanks for listening. I'd be happy to take any questions.
This is a little off point because it's not necessarily related to adolescent exoplanets, but I'm interested in this tabby star that's reducing the light coming
Oh.
from it, and they're talking about this giant alien structure.
The alien megastructure one?
Yeah. What is going on?
So for those of you who aren't familiar, this was detected via the transit technique. And you know, I mentioned essentially what happens with the transit technique is you have some constant level and then there's a dip and then it comes back, right? So there's a star that has like these crazy aperiodic, really deep dips, this whole series of them. And people have been trying to figure out what the heck it is. And I've yet to hear a convincing explanation for what could be causing it. So people were like alien megastructure, you know, like a partially constructed Death Star, like, you know, periodically parts of it transiting the star. I would guess that there's a logical explanation that doesn't invoke alien civilizations, but I have yet to hear a really good convincing one.
Yeah, but it
Either way.
seems like the scientists are really confused about this.
It's very confusing because they're very deep and sort of semi-periodic. It could be a stellar phenomenon, but it doesn't have the pattern that we would expect for that. So yeah, it's not my field, but I have not heard anything super convincing. Yeah.
The presentation represents one exoplanet on a star. Are you anywhere close to finding stars that have a solar system?
Yeah, actually, let's see, do I have it in here? The second successful direct imaging detection, this is another nice thing about direct imaging. Let's go to maybe, I don't know. Another interesting thing about direct imaging, so here's one. So this is the HRE 799 system, which was the second successful direct imaging detection. And it actually has 4 planets. One of them is outside of the field of view of GPI. So it's way out here. But these 3 are all orbiting the same planet. And similarly, both radial velocity and transiting exoplanet detection methods have successfully found multi-planet systems. It's difficult, you know, the signals are often blended, and you know, we find the big thing first. The big things are easy to find, the Jupiter-like planets, but the smaller things are harder and harder to find. So there are a variety of ways that we've been able to find these multi-planet systems, and they appear to be fairly ubiquitous.
What's the range of distance from either the sun or the Earth, whatever, the center of our solar system, from the range of distance where we're discovering the stars with exoplanets?
So it depends very strongly on method. So for direct imaging, all of the successful detections so far have been within, I don't know, let's go to like, have been kind of, all of these guys are within about 50 parsecs from the sun, so 150 light years or so. The transiting exoplanets are almost all from the Kepler field, which are preferentially about like hundreds of parsecs. So several hundred parsecs. The microlensing technique, these are all over the place, but they can be on the other side of the galaxy. I sometimes debate whether to talk about microlensing at all because, well, I'm biased, but it's my least favorite of the techniques just because there's absolutely no possibility of characterizing exoplanets via microlensing because that event is so rare and unrepeatable that you can only detect it once. You detect only its mass and separation. You could never follow it up.
I understand, if I can interrupt for a second. I think I read somewhere, you know, and we're trying to determine the age of the universe, and that, again, it's a great opportunity for me to display my ignorance, but isn't this somehow related in terms of the distance that we can detect, which would thus correlate to the age of the whatever we're detecting, that the universe is at least 14.7 billion years old?
So constraints on the age of the universe don't really come from the exoplanet field just because, so, you know, we measure the ages of stars. Actually, it's very hard to measure the ages of stars, but an active galaxy, an active spiral galaxy like our Milky Way is constantly forming stars, right? So we find stars that are 1 million years old, we find stars that are 8 billion years old. the Milky Way galaxy is not an original galaxy, right? So it's difficult to place any constraints on the age of the universe from exoplanet detections and aging stars in particular. But there is a whole field of astronomy related to cosmology, to determining things like the age and shape and structure of the universe, and there are other ways to constrain that. But of course, there is the idea that the oldest star that we can possibly detect is a constraint on the age of the universe.
But isn't it also felt that all of the galaxies were relatively, in terms of the age of the universe, were created within the same small space relative to the age of the universe?
Yes.
So that we would approach that by some of these techniques that can go out to the edge of the Milky Way, basically.
Yeah, so the much more powerful constraints come from techniques and images. So we can't detect any exoplanets outside of our own galaxy. And the extent of our galaxy, light that comes from the edge of our galaxy is only 50,000 years old.
Oh, okay.
Light that comes from distant galaxies can be billions of years old, right? So we're looking in much more distant space than anything that we're discovering with any of these techniques.
Okay, thanks.
I'm sorry to interject. We're over time, so I just wanted to let people know, because I know people have to get on to other programs. And
Sure. I'm also happy to stick
So
around and
sorry.
answer questions.
Yeah.
So, thanks.
Thank you.